You think the Mandelbrot set is just a picture, a pretty image you've seen 1,000 times, psychedelic colors, no? Spirals within spirals. Maybe you had it as a screensaver in the 90s. Maybe you saw it in a documentary about chaos or fractals. Beautiful, mysterious, something mathematicians made with computers. Fine. But what is it really? What are you actually looking at when you see that famous black shape with its bulbs and tendrils and this infinite coastline? Most people have never really thought about this. They see the image and think, fractals, infinite detail, the same pattern repeating forever, and they move on. But that's not an answer. That's just repeating words you've heard somewhere. When you really ask what the Mandelbrot set is, when you dig into why the zoom never ends, you discover something so strange, so fundamentally different from anything else in mathematics that it changes how you see structure itself. The Mandelbrot set isn't a picture. It's not an image someone drew or rendered. It's not stored anywhere. It's a mathematical process that generates structure at every scale you care to look. And here's the part that should break your intuition. The deeper you zoom, the more structure appears, not less. More. New structure. Structure that wasn't visible before, structure that couldn't have been predicted from what you saw at larger scales. Let me show you what I mean. Start with the simplest possible thing, a rule, one rule. Take a number, square it, add another number. That's it. Z goes to Z, squared plus C. The most elementary operation you can imagine. Squaring and adding. A child can understand it. Now here's the question. You pick a number C, any complex number on the plane, you start with Z equals 0. You apply the rule. Z becomes C, you apply it again, Z becomes C squared plus C, again and again and again. Why? What happens? For some values of C, the numbers stay small. They bounce around near 0 forever. Bounded, contained, stable. For other values of C, the numbers explode. They grow larger and larger without limit. They escape to infinity. The Mandelbrot set is simply the collection of all those C values where the numbers don't escape. The black region, the points that stay bounded forever under iteration. That's it. That's the entire definition. One rule, iterate, check if it escapes or not, color it accordingly. Now stop and think about what just happened. We didn't draw anything. We didn't design anything. We didn't specify any spirals or bulbs or tendrils. Or we just asked the question, for which points does this simple process stay bounded? And out of that question, purely from that question, emerges this impossibly intricate shape. Bulbs attached to bulbs the sauce that spin into other spirals, filaments so thin they seem one-dimensional, yet zoom in and they bloom into full two-dimensional complexity. Seahorses, elephants, lightning bolts, an entire zoo of forms, none of which we specified, all of which emerged from one rule. This is what people miss when they call it a picture. A picture is something you create. You decide what goes where. You choose the shapes. The Mandelbrot set isn't created. It's discovered. It was always there, implicit in the rule, waiting for someone to look. But here's where it gets stranger. You've probably heard that fractals are self-similar. The same pattern repeats at every scale. Zoom in and you see smaller copies of the whole. This is true for simple fractals. The Sierpinski triangle, the Koch snowflake, zoom in exact copies appear. The Mandelbrot set doesn't work like that. And this is crucial. When you zoom into the Mandelbrot set, you don't see exact copies. You see approximate copies, near self-similarity, not exact self-similarity. You encounter baby Mandelbrots, yes, tiny versions of the whole set embedded within it. But each one is slightly different, surrounded by different spiral structures, connected by different filaments living in a different neighborhood that colors its character. Think about what this means. At every scale, there's something familiar. You recognize the shape, you've seen it before, but at every scale, there's also something new. Details you couldn't have predicted, variations you've never encountered. The set quotes itself, but never repeats itself. This is why the zoom never ends. If the Mandelbrot set were exactly self-similar, zooming would eventually become boring. You'd see the same thing again and again. But because it's only approximately self-similar, every zoom reveals new structure, new arrangements of old themes, familiar motifs in unfamiliar configurations. It's like a symphony that uses the same instruments but never plays the same melody twice. Let me make this concrete. Pick a point on the boundary of the Mandelbrot set. The boundary is where everything interesting happens. Inside the set, points are stable. Outside the set, points escape. But on the boundary, you're right at the edge. The tiniest change in position can flip a point from stable to escaping. Now zoom in on that boundary point. What do you see? You see the boundary getting more complex, not simpler. You see filigree, you see spirals nested within spirals. You see the edge becoming more and more intricate the closer you look. In ordinary geometry, when you zoom in on a curve, it gets simpler. A circle magnified enough looks like a straight line. A coastline zoomed in enough becomes individual grains of sand. Smoothness emerges from roughness at small scales. The Mandelbrot set does the opposite. Zoom in and it gets more complex, always, without limit. There is no smallest scale at which the boundary becomes smooth. There is no resolution at which you've seen everything. The complexity goes all the way down. Why? What's generating this infinite structure? The answer lies in what I call roughness, but not random roughness, structured roughness, roughness that follows rules. Think about iteration. You apply the rule once, twice, 1,000 times, 1,000,000 times. Each iteration adds information. Each iteration separates points that were close together. Points that look identical at coarse resolution turn out to have completely different fates at fine resolution. Near the boundary, this separation is extreme. 2 points might be arbitrarily close, so close that no computer could distinguish them, yet one escapes to infinity and the other stays bounded forever. The iteration process magnifies these microscopic differences into macroscopic outcomes. This is sensitive dependence on initial conditions. The same phenomenon that makes weather prediction impossible beyond a few days. The same phenomenon that underlies chaos. But here, instead of making things unpredictable, it generates structure. Every time you zoom in, you're asking, among these points that looked similar before, which ones escape and which ones stay? The answer is never simple. The answer is always intricate because the iteration process has had time to separate them in complex ways. Here's another way to think about it. The Mandelbrot set exists at the intersection of order and chaos. Inside the set, behavior is orderly. Iterations stay bounded, often settling into periodic cycles. Outside the set, Behavior is also orderly in its way. Iterations escape growing without bound. But on the boundary, you're between these two regimes. You're in the zone where tiny changes produce dramatically different outcomes. This zone isn't thin, it isn't a simple curve, it's infinitely intricate, fractal, because the transition from bounded to unbounded is itself infinitely complex. Now, you might ask, why should I care? Why does this matter? It's just mathematics, just abstract numbers and the rules. What does it have to do with reality? Everything. Look at nature. Really look. What do you see? Coastlines that look jagged at every scale. Not smooth curves that straighten when you zoom in, but irregular boundaries that reveal new irregularity the closer you look. Trees whose branches branch into smaller branches that branch into smaller branches still, each level of branching following similar but not identical patterns. Mountains whose surfaces are rough at every scale. Zoom in with a microscope and the roughness doesn't disappear. It transforms into different roughness. Clouds, lightning bolts, blood vessels, river networks, the distribution of galaxies in the universe. None of these follow the rules of classical geometry. Classical geometry deals with smooth shapes, circles, spheres, planes, shapes that simplify when you zoom in, shapes characterized by their dimension, one-dimensional lines, two-dimensional surfaces, three-dimensional volumes. But natural shapes don't simplify when you zoom in. They maintain their complexity across scales. They have structure at every level of magnification. And they often fall between dimensions, not quite one-dimensional, not quite two-dimensional, something in between. Fractal, the Mandelbrot set, taught me this, not because it describes any particular natural phenomenon, but because it shows that simple rules can generate infinite complexity. That iteration, recursion, feedback can create structure at every scale without limit. Before I studied these objects, most scientists assumed that simple rules produce simple outcomes. You want complex behavior, you need the complex rules, you want rich structure, you need elaborate mechanisms. The Mandelbrot set demolishes this assumption. One rule, Z goes to Z squared plus C. Apply it repeatedly. Out comes infinite complexity. The rule couldn't be simpler. The outcome couldn't be richer. This principle extends far beyond pure mathematics. Think about how markets behave. Fluctuations at every time scale. Daily movements that look like monthly movements, that look like yearly movements. Self-similar, but not identical. Infinite intricacy emerging from the interaction of many simple decisions. Think about how turbulence works. A smooth flow becomes unstable, breaks into eddies, eddies within eddies, structure at every scale down to molecular dissipation. Simple fluid equations producing infinite complexity. Think about how languages evolve, how cultures develop, how ecosystems arrange themselves. Pattern within pattern, scale within scale, complexity emerging from simplicity through iteration and feedback. This is what I spent my life trying to understand, not specific applications, but the underlying principle, the mathematics of roughness, the geometry of the irregular, the science of complexity. And the Mandelbrot set is the purest example, a window into how simple iteration generates infinite structure. Let me tell you something that still amazes me. When I first plotted the Mandelbrot set on a computer in the late 1970s, I didn't know what I would see. I'd studied similar mathematical objects. I had conjectures, but I didn't expect this. I remember zooming in for the first time, seeing the boundary get more complex instead of simpler, finding baby Mandelbrots in unexpected places, discovering spiral structures that seemed to have no end. I zoomed deeper and deeper. Every level revealed new forms. Every magnification brought new surprises. The set seemed alive, generative, creative in a way mathematics rarely is. And here's the key point. I wasn't creating anything. I was discovering. The structure was already there and encoded in the simple rule. I was just the first to look. This is what makes mathematics so extraordinary. These objects don't depend on me, on humanity, on Earth, on the universe. The Mandelbrot set would exist even if no one ever discovered it. Its properties are eternal, unchanging, absolute. We access them through computation and proof, but we don't create them. When you zoom into the Mandelbrot set, you're not generating images. You're exploring a mathematical continent that exists outside of time and space. Every detail you find was always there. Every spiral, every bulb, every filament has been waiting since before the Big Bang for someone to look. Some people find this cold. Abstract mathematics removed from human concern. I find it the opposite. The most direct connection we have to something beyond ourselves, something permanent, something true. Now back to the original question, why doesn't the zoom ever end? Because the Mandelbrot set encodes a process, not a thing. Every point you examine requires infinite iteration to determine its status. Does it escape or not? You can never know for certain by looking at finite iterations. You can only approximate. And because the boundaries were bounded and unbounded, points interleave in infinitely complex ways. No matter how closely you look, there's always more interleaving to discover, always more points to separate, always more structure to resolve. The zoom never ends because the process never terminates, because iteration goes on forever, because the question, does this point escape, has infinitely nuanced answers along the boundary. Here's the deepest thing. Classical geometry loves flat spaces. Euclidean geometry assumes that at small enough scales everything looks flat. Smooth, regular. This assumption underlies all of classical physics, classical engineering, classical mathematics, but the Mandelbrot set suggests a different possibility. What if structure persists at all scales? What if roughness never smooths out? What if complexity is fundamental, not derived? This would change everything about how we model the world. Instead of smooth approximations that break down at fine scales, we might need rough models that maintain their character across scales. Instead of dimension as a whole number, we might need fractional dimensions that capture the intrinsic complexity of natural shapes. I don't have all the answers. No one does. But I believe the Mandelbrot set points toward a new geometry, a geometry adequate to the rough, irregular, complex world we actually live in. Yeah? A geometry where infinite structure is the rule, not the exception. When you look at the Mandelbrot set, you're not looking at a picture. You're looking at a doorway into a mathematics that embraces complexity instead of fleeing from it. A doorway into a science that sees roughness as fundamental, not as noise to be averaged away. A doorway into a new way of understanding the endless structure of nature itself. The zoom never ends because the universe never simplifies. At every scale, there's more to see, more to understand, more to discover. The Mandelbrot set shows us that simple rules can generate this infinite richness. That complexity isn't the opposite of simplicity, but its offspring. That iteration, the most elementary of processes, can create worlds within worlds without limit, and that changes everything. Not comfort, not familiarity, truth.